Welcome to this explainer. Okay, if you're a college student right now and you're just staring at this massive, heavy compiler textbook, maybe the famous Dragon book or Loudon's compiler construction, I want you to just take a deep breath. Let's step back from all that dense mathematical notation and the thick jargon for a second. Today, we're going to clear the air and completely deconstruct top-down parsing. We're taking it slow, giving the concept some real visual breathing space, and we're going to figure out how this actually works. Sound good? Let's dive in. Have you ever stopped to really think about the everyday magic happening right there on your screen? I mean, how does your computer actually read the code you write? You sit down, you type human-readable words like if or for, or even just a simple math expression like 9 minus 5 plus 2. Now to the computer, initially, those are just raw, totally meaningless characters. Yet somehow, the machine groups those characters together into meaningful tokens, and it simply understands the structure of your logic without completely panicking. So, how does it actually make sense of our text? Listen, if learning how this happens feels overwhelming, I want to validate that for you right now. You are in very good company here. Even the classic compiler's text by Aho, Lam, Sethi, and Ullman openly admits parsing is one of the most fundamental problems in all of compiling. It's a massive hurdle. Figuring out if a string of text actually conforms to the rules of a programming language, it's like a giant, highly complex puzzle. But hey, we're going to break it down gently today, just one simple idea at a time. Before we get completely lost in the weeds, gently remind yourself that at its absolute core, a compiler is really just doing translation work. It takes your source program, your high-level ideas written in C or Java, and it passes it through this sort of black box to produce an equivalent target program. Usually that's machine code. Parsing is simply the front end of that black box. It's just trying to figure out the grammatical structure of your sentences so it can translate them accurately. Section 1. Growing trees from the sky. So to understand how compilers actually map out grammar, computer scientists use a pretty natural metaphor, growing trees from the sky downwards. Parsing is essentially just the problem of taking a string of text and organizing it into a branching structure called a parse tree. A parse tree traces out the exact steps needed to derive your string of code from a broad starting symbol. Think of it kind of like diagramming a sentence back in elementary school. You start with the big concept of a sentence, which then branches into a subject and a predicate, and those branch into nouns and verbs, right up until you finally reach the actual words on the page. Compilers generally build these trees in one of two ways. And honestly, this brilliantly illustrates the big divide in parsing theory: top-down versus bottom-up. Top-down parsing starts at the root, that grand overarching idea at the very top of the tree, and branches downward toward the actual text, which we call the leaves. Bottom-up parsing does the exact reverse. It starts with the text at the bottom and builds upwards to the root. Now, while bottom-up can definitely handle a wider variety of really complex grammars, today we are just focusing on the calm, highly intuitive flow of top-down parsing.
Section 2. One step at a time.
Okay, so how does a top-down parser actually take those steps downward from the root to the leaves? Well, you'll almost certainly hear the term recursive-descent parsing. Now, I know it sounds like this scary, highly advanced algorithm, but I want you to just think of it as an intuitive, one-step-at-a-time method. It's simply a top-down approach that relies on small, dedicated procedures for every single grammatical rule. It literally just delegates work. If the parser is looking for an if statement, it calls a specific procedure designed just for if statements. If it needs an expression, well, it calls the expression procedure. The absolutely crucial point here is how wonderfully simple the execution of these procedures really is. Inside any given procedure, the parser just does a few basic things. First, it chooses a grammatical rule to apply. Second, it checks the current symbol in your code to see if it actually matches that rule. And third, if it matches, it advances the input to the next symbol. It's beautiful in its simplicity. I mean, this is basically how you and I naturally read sentences, just scanning left to right, verifying each word against what makes grammatical sense. In fact, this method is so natural that it's widely beloved by programmers everywhere. The source material by Loudon even notes the flexibility of recursive-descent parsing makes the method of choice for hand-generated parsers. Because top-down parsing maps so perfectly to how we logically think about code structure, programmers often just write these parsers entirely by hand, rather than relying on automated generation tools. It gives them complete, total control over the whole process. Section 3. Looking ahead to build. Now, you might be wondering, when the parser is standing at a branching point in the tree, facing multiple possible grammar rules, how does it know which rule to pick without getting completely lost, or constantly having to guess and backtrack? Well, this is where we introduce the concept of the predictive parser. A predictive parser attempts to predict the correct next construction in the parse tree by using what we call a lookahead token. Imagine reading a sentence. If you see the word the, you can pretty safely predict that a noun or an adjective is coming up next. The top-down parser does exactly this. It peeks ahead at the very next symbol in your code to decide precisely which path to take down the tree. In compiler terms, this is often called LL1 parsing, where that one simply means it looks ahead exactly one symbol. And this brilliantly illustrates exactly why predictive parsing is so absolutely vital for real-world programming. In theory, sure, a parser could just guess a rule, and if it fails, back up and try another. But that backtracking, it can require exponential time, or order n-cubed time, which is painfully, completely unworkably slow for a computer. But by designing our languages so the parser can just look ahead one terminal at a time, we eliminate that exponential backtracking entirely. The parser runs incredibly efficiently in a single, calming, linear left-to-right scan.
Section 4. A calmer way to code.
Okay, let's bring this all together. When you're buried deep in compiler theory, studying finite automata, context-free grammars, and syntax trees, it is remarkably easy to get overwhelmed. But if we strip away all the advanced math and those complex diagrams, what do we actually have? Compilers are simply machines reading text left to right, just trying to make sense of the world. They use top-down parsing to gently break big ideas down into smaller ones, carefully peeking ahead one word at a time to stay on track. Literally, exactly like we do. So, I'm going to leave you with this final, very low-pressure thought. If parsing is fundamentally just the act of teaching a computer how to read human structure, well, what new ideas will you teach it to understand next? Thank you so much for joining me for this explainer. I really hope stepping back from the textbook today has left you feeling a bit more capable, a little more centered, and highly curious to dive back in and learn more. Catch you next time.